Welcome to new problem solving session. Here we have a problem with problem based on rolling with slipping, and so we got a wheel of radius r rolling with slipping on a horizontal surface. The modulus of the velocity of the upper point of the wheel rim A. Perhaps it is the topmost point of the wheel lying on the vertical diameter is equal to VA. That's right. The modulus of velocity of the point of the wheel rim B. This is another point lying on the horizontal diameter. Okay, is equal to VB equals 5 times of VA. We don't know exactly the direction of this direction of velocity of this point, but we do know the magnitude of velocity of this point B. So we have to determine the angular velocity of rotation of the wheel B and the velocity of its center V0 and position of the instantaneous center of rotation. So we need to find out three things. Okay, and we will check whether they are related or not. So I have drawn a picture for you, and the picture at the screen is this. You can see the wheel, point A, point B, and a possible instantaneous center of rotation. I don't know exactly where it is, but there is a possible instantaneous center of rotation. This is point B, this is point A, and there is a reference system, XY axis. I have drawn the XY axis of a Cartesian coordinate system, and we will use it as a laboratory inertial reference system. This reference system attached to the earth, and here are a few things if you can see it yourself. But well, the setup is ready, and we need to move. That means we need to solve the problem. And you can see here, if no, this was basically provided in the problem statement that the velocity of the center of this wheel is V0. Though V0 was not provided, we need to find it, but its velocity was named V0. So that's right. And here is a point A having velocity VA, and here is point B, and its velocity is VB. And why VB is lying in this direction is you might be curious to know, and I'm going to give you an answer. Despite we already have a coordinate system, a lab frame, I'm going to set up another reference frame, this time moving with the speed V0, and this is basically center of the wheel. So if I place an observer here at this point, so it can only watch the rotation of the wheel, and that is, if the angular velocity of the wheel is omega and its radius is r, then for this observer, point A and B will be moving with velocity omega r only, nothing else. So for this observer sitting at the center of the wheel, the velocities of each and every point of the wheel rim is simply equal to omega multiplied by r. So for this observer, velocity of point A is omega r, velocity of point A for this observer with respect to O, and the observer itself is moving with velocity v naught in the same direction, in the direction of omega r with respect to the ground. So velocity of A can be simply written as v naught plus omega r and nothing else. And we have used the principle of superposition of velocities to find this. This is the velocity of center of the wheel with respect to ground, and this one is the velocity of point A with respect to the center of the wheel. So we added them since they were in same direction, so we simply avoided using the vector notation, and we got the velocity of A in a lab frame. In the similar manner, we can also find the velocity of point B, that we should write the velocity of point B with respect to an observer at the center of the wheel plus velocity of the observer itself. So you can see here, with respect to this observer, B moves in this direction and its magnitude of velocity is omega r, provided omega is the angular velocity of the wheel and r is its radius. And velocity of this observer O sitting at the center of the wheel is v naught itself. So that, and these are perpendicular, so velocity of point B can be simply written with magnitude equal to Vv equals v naught square plus omega square r square. So we got the velocity of point A and velocity of point B with respect to the ground in the lab frame, and we have just introduced other notations like or other unknowns like alpha. And here you can see that alpha is the angle between velocity of point B and direction of motion of the wheel center v naught. And here is something I have this point has been designated by a letter M. So what is this basically? Since this is the velocity of B and velocity of B seems to be perpendicular to this line, so that means for this point B is moving in a circle. B is performing a circular motion with respect to point M, so that MB being its radius. So what exactly M may be? This is basically the instantaneous center of rotation of the wheel. Only that case you can say that velocity of point A is perpendicular to the line joining M and A, that is MA, and it's moving in a circle around it with a radius MA, and B in the same manner is moving in a circle with velocity VB and radius MB, and all other points of the on this wheel rim are doing the same. If this point M is supposed to be the instantaneous center of rotation of the wheel, so later comes the geometry, and this is the horizontal line and this is the line of VV, and this line is perpendicular to VV and this is vertical, so this angle should also be equal to alpha. and we did what could we do, and I think here that we can write tan alpha in two different manners. In this figure, tan alpha is simply perpendicular, that is omega r by base, that is simply omega r by v naught. And in this figure, tan alpha is again written in this length structure. Tan alpha can be written as perpendicular by base, and perpendicular is radius and base is this length. And in this laboratory system, I have provided this instantaneous center M a coordinate ym. Ym is basically the y coordinate of the instantaneous center of rotation. So this length will become ym, and the whole length, this whole length is from here to here. Whole length is the radius of the whale. So basically the length we are looking for, that means this length is r minus ym. So we can write tan alpha in terms of ym as well, and that tan alpha is equal to r minus ym. So I did all the things that can be done from this figure, that can be found from this figure. Now we need to we had a job to find the value of omega, the angular velocity of the whale. So what can we do? So I'm going to use these two equations, equation number 1 and equation number 2, and from 1 I'm hoping to, and there are two unknowns in this structure. In fact, there are two unknowns in these equations. One is v naught and another one is omega. So what I'm planning to do to eliminate omega and try to get an equation in form of, I'm trying to eliminate v naught. In fact, what I'm telling, I'm trying to eliminate v naught and hope to get an equation in terms of omega using equation 1 and 2, and hopefully I can do this so that from equation 1 v naught can be written simply as va minus omega r, and I'm going to put this value of v naught into equation 2 so that I can get vb square equals v naught square. That means va minus omega r square plus omega square r square, which was already there. So if I break the square, I can get va square plus omega square r square minus twice va omega r and plus omega square r square. So the next thing, you can find it, and why not, I should find it. So it becomes va square plus twice of omega square r square minus 2 va omega r, and va and vp is already given. We know the value of r is also given, so I only need to find the omega from this equation. So I'm going to get a quadratic equation in omega, and why not, I can get it. So that I would like to write this as 2 omega square r square minus twice va omega r and plus va square minus vb square equal to 0. So that if I needed to get a quadratic equation in omega, So I'm going to divide the whole equation by 2r square, so that I can get here omega square minus VA upon R multiplied by omega plus VA square minus VB square by 2R square. And this is one equation. And since it is a quadratic equation in omega, so I need to find the values of omega by using the formula for quadratic equation, and this is minus b by minus b plus minus b. So I can write here omega equals VA upon R plus minus under root b square, VA upon R square minus 4AC. C is simply VA square minus VB square by 2R square. I can get this 2 cancelled out, divided by 2A. So I got omega, and I can simplify it writing omega equals VA upon R plus minus VA square by R square minus minus 2 VA square plus 2 VB square divided by R square, so that I can get here divided by 2. 2 is always there, divided by 2 is always there, so I can get here I can get a VA upon R from here. So what I am going to get finally, omega equals VA upon 2R plus minus 1 upon 2R 2 VB square minus VA square. So, and I can put here VB equals 5 VA, so that I can get omega equals, in terms of VA upon 2R plus minus 1 by 2R, and this result is simply nothing but 7 VA, because the term under square root is 49 VA. So I'm going to get this thing, omega equals VA upon 2R plus minus 1 by 2R, 7 VA. This is not yet complete, but still I can get two values of omega, two roots of omega as omega 1 and omega 2, and omega 1 can be found out by using this plus sign, and if I use this plus sign, I am going to get 8 VA upon 2R, and omega 2, the second root of omega, I can get by using this minus sign, and this is negative, minus 6 VA upon 2R. That means we got two values of omega, like 4 VA upon R, and second value is minus 3 VA upon R. So we got two values of omega 1 and omega 2, and since V naught is equal to VA minus omega R, yeah, this was equation 1, V naught equals VA minus omega R. So we can also get the two values of V naught itself by using omega 1 and omega 2. So the first value of V naught I get is VA minus 4 VA upon R multiplied by R, and that is equal to minus 3 VA. Now the first value of V naught, And in the similar manner, second value for V0 we can get by using VA minus, the omega 2 is minus again, so I can write here omega 2 is minus, so there will be a plus sign here, so that I can write 3 VA upon my R multiplied by R, and I get 4 VA as the answer for the second value of V0. So these are two values of V0, and we needed to find out the position of instantaneous center of rotation, that was M, point M, and its y coordinate was ym. So I had two values of tan alpha. I got them. Yeah, here it is. Tan alpha equals omega r by V0 and tan alpha equals r by r minus ym. So I have two values for V0 and omega. So equating these two tan alphas, I can get the two values of instantaneous center of rotation. That means in two different cases. So I can write here omega r by V0, and that is equal to r by r minus ym, and so that I can get omega multiplied by r minus ym equals V0, and that means I can get ym equals r minus V0 by omega, and this is the result I need to find out the y coordinate of instantaneous center of rotation. So in the first case I am going to use the first values of V0 and omega, that is V0 1 and omega 1. So ym1 is simply r minus V0 1 minus omega 1, and then that becomes r minus V0 1 minus 3VA, that is equal to minus 3VA by omega 1. Omega 1 is 4VA upon r, so it's 4VA upon r, and solving this I can get here r plus 3 by 4r, so it's ym1 I get is 7 by 4r. That's right, I got the y coordinate of instantaneous center of rotation, and I can still get another value of instantaneous center of rotation in case of second values of V0 and omega, and that I should write r minus V0 2 divided by omega 2, and that means r minus V0 2 was 4VA divided by omega 2 was minus 3V0 by r, minus 3V0 by r. So this is again, numerator is again 7, but denominator this time is 3, so it gets 7 by 3 r, the values. And let me show you the pictures. They are the motion, the whole motion will look like the pictures of those pictures of the motion the wheel is undergoing in these two, for these two different values of omega. Let me show you the picture, and here you can see there are two pictures. In the left picture, omega 1 is simply 4VA upon R, and V naught is negative, that is minus 3VA, and YM1 is 7 by 4R. So this is VA, and if this one is VA, omega, this is V naught. V naught is negative, that means 3 times of VA, but towards negative x-axis, so that V naught is towards negative x-axis and omega is positive as usual clockwise. So this is the velocity of point B, and you can see here what is the value of y coordinate of the instantaneous center of rotation. This time this is less than 2r, because 7 by 4 is less than 1. So 7 by 4 is not, 7 by 4 is less than 2. So this length is, but this length, but 7 by 4 is less than 1 and less than 2. So here it is the instantaneous center of rotation ym in the first case. Second case, when let me see, second case omega 2 is negative, that is minus 3 VA upon R, and V naught is positive, and this is 4 VA, and in this case the instantaneous of center of rotation is 7 by 3R, that is greater than 2. So you can change the, you can see the change in direction of omega from here in comparison to the figure on the left, and VA is again in this direction. So omega R is in this direction, and V naught you can see here. Again you can easily see that velocity of point B, how I have drawn the velocity of point B, the arrow of velocity of point B, and of course the instantaneous center of rotation is here, that is outside the wheel. So it can be inside or outside the wheel. It all depends on the given condition, and though in case of rolling without slipping, it always lies, the instantaneous center always lies at the point of contact of the surface with the wheel. But in other cases, when the wheel is rolling with slipping, you cannot be sure. You have to find the situation in every case. And what should be the procedure? The procedure should be simply, you have to go with 2 observers. Always put an observer at the center of the rolling body, and another associated with the ground. And simple things you need to use, simple geometry, the principle of superposition of velocities, and everything else will be fine. Thank you very much.